Good morning and welcome to the grade 11 Physical Sciences Newton 2 overview. We have Newton 2 questions in our test and exams. Let's look at the steps, how to basically work these out with like an overview kind of framework. So, first of all, you need to know your trig. You need to know your trig rules. If you don't know your trig rules, end this video right now and go figure out what those rules are. And I'll put them in quick. They are SOHCAHTOA, that is for a right angle triangle. Later on you will be learning about the sine rule and the cosine rule. Sine rule is very effective, but SOHCAHTOA, if we're looking at this angle up here, I'll use the one we don't want to look at. But if that angle is the one you're looking at, you look at the opposite side, which is here. This is opposite, this will be adjacent, and this will be our hypotenuse, because our hypotenuse is the line across from that 90-degree angle. So SOHCAHTOA, sine of that angle will be opposite over the hypotenuse, so op over hype. Ka is cos of that angle, that specific angle will be that adjacent side divided by the hypotenuse, so that'll be cos of whatever that angle is adjacent over hypotenuse, whatever those values are. And TOA is tan of that angle will be opposite this side, opposite to the angle, opposite side to the angle over hypotenuse. And that's how those rules work. If you were to use this angle here, let's just call it theta so we don't make it a dot. If you're going to talk in terms of theta, now this will be adjacent. The adjacent side, the attached side, and this will be the opposite side. All right. Next step is step 2. Draw a free body diagram. I don't care how you feel. I don't care how much time you've left in that test. You will draw a free body diagram because they explain everything. And don't make a mistake in it, because if your free body diagram has an error, everything afterwards has an error, and we don't mark positively from a buggered up free body diagram. So that will be step 2. Always draw that free body diagram. And step 3 is the actual Newton 2, which is F net is equal to MA. So you'll always start with that statement in every single Newton 2 or problem. Now, this can break up into many things. So there are various, but I also said in the correct plane in terms of your free body diagram. So let me quickly draw a made up one here. Here's our made up little free body diagram. We have an applied force to the left, we have tension to the right, we have a friction to the right, Fg downwards, and a normal force upwards. We assume it's on the surface. So let's just say they're asking us to determine the tension force. So in what plane are we dealing with? We are dealing with this plane. We are going to ignore these two unless sometimes you have to work out friction and you sort of need this value. But anyway, like let's not overcomplicate this, but we will work in that plane. So going up here by this number 3 here, we divide this, we write down F net is equal to MA. I don't care if you know what the acceleration is. I don't care if there is one or not one. We will determine later if that's 0 or some other value. Now, F net, we will be filling in, breaking up that F net into these 3 components. You have your tension force, you have your frictional force, they're both going to the right, and your applied force is going left. But we have to choose a direction as positive. Very important. That's actually the first thing we should state. So I'm going to write that out. We say then, left is positive or right is positive. So let's just be funny and say that left is positive. You have to write this down so that you don't make stuff-ups. So we're going to break this F net up. FA is a positive value, so we say FA. We're adding then the FT, but it's going to the right, so it has to be stated as a negative FT. And then your frictional force also going to the right, that's a negative F, and that will be equal to MA. We don't do anything at A, we just leave it as is. We don't make it positive or negative, we just leave it as is for now. All right. Right, so it's very important to get this. This should just be a random layout. We can just simplify this and MA. All right, so usually you will have one unknown and the rest you'll know, or you actually, yeah, unless you're dealing with those simultaneous equation questions. I'll just do a few overviews of those just now. But if your applied force is in an angle, you'll have a triangle you have to deal with, and then you have to use your trigonometry that you obviously know how to do, right? Anything at an angle that's not directly horizontal or vertical will have that type of thing. Friction can also be sometimes have that equation. Fk is mu kn, and that's when you'll have to bring in your normal force. Sometimes they don't give it, they just give Fg, and if they're directly opposed or just directly on a surface that's not being pulled at a certain angle, everything is nice and horizontal and vertical, your Fn will then be equal in magnitude to your Fg. Opposite direction, but the magnitude will be equal. All right, so you can work out that Fk is mu kn, which is the frictional coefficient. They'll give you some value, 0.2 or something, and then you can work that out as a little sub thing, or you can just substitute it in there if you want. All right, so let me just do a few overviews of what type of questions can be asked, and hopefully it helps you to see. Alrighty, so I don't know exactly where I stopped. I paused that recording. I think it was here. So we have some types of questions or examples of types of questions you can get in your test. So according to our steps, we said we must know, okay, let's start from step 2 because we all know trigonometry, right? Step 2, if you got to, what was step 3? Oh, step 3 was F net is MA. You always have to start with this in an exam and then break up your F net into its various components. Right, now, here's the first type. Okay, so there's this guy, he's pushing down on this object A and it's moving to the right. So it's being pushed at an angle downwards into the ground, and this object is now moving to the right. So how does our and there's we're just going to assume friction exists everywhere. If it does not exist, then it should tell you. So let's take a look. First of all, friction, this thing's moving to the right. I'm just going to write the velocity is to the right. It's moving to the right. It's accelerating. Yeah, let's just assume it is also. But your friction will be then automatically to the left. You have an Fg, a weight, always, and you have a normal, and because it's on a surface. So you have friction, and to the right you have, oh wait, this guy is pushing it at an angle of 40 degrees. So here's the hard part for some people to understand. But this guy's going to be pushing down like this vector. Now you have to decide, is that 40 degrees here or is that 40 degrees there? That is actually the thing that catches people. So what I'm going to do is just draw this picture more detailed. So I'll show you how to identify which angle goes where. There we go. So I just drew that vector there, that applied force vector. And what we know is that when it hits that block, it's hitting it at 40 degrees to the horizontal. But that is at the head part. But using alternate angles, the tail part will have a 50 degree ratio of angles over there. So looking over here and over here, we know that the 40 will be up there. This is quite a tricky one for some people to understand, but that is the trick. And so now we know how to identify that. All right, and from there, if they were to, this is your applied force, if they were to ask you, calculate there's another important thing I want to show you here. In the vertical, the vertical plane, yes, so looking at the vertical plane, that plane, we actually have 3 vectors in operation there. So what I'm going to do is, I'm going to double up this drawing to the alternative method. Alright, so there I drew it. These are actually the 2 options that you can draw in the exam, but taking a look at this one, there's something very important to note, that the normal force will be equal to how can I explain this? The normal force, or let's put it as the positive side will be equal to the negative side, or the positive y-axis, or all the vectors that are going up will be equal to the vectors going down, assuming obviously these blocks that we are dealing with, or these objects, are not accelerating upwards or downwards. Usually it's left or right. So there's no movement going up or down. So therefore we can just assume, oh, you can just actually just do this. I'll show it both ways. F net is 0, or we can say, because we know that F net is 0, we can say Fn is equal to Fay plus Fg. Break this up into its components here. Let's just take up as positive in this case. So we have Fn plus a negative Fay, close that bracket, that is negative, plus a negative Fg, and that'll be equal to 0. And if you see, if you just solve for this thing, we have Fn is equal to Fay plus Fg, which is, go figure, the same as this, because you know the F net in the y-axis is 0. There's no acceleration in the y-axis. All right. Yes. So if we look at this diagram here quickly, which is larger, your Fn or your Fg? Which is larger, your Fn or your Fg? There's a few ways to look at this, but if you look at it like this, these two together must be equal to Fn. So in this case, logically, your Fn will always be larger than your Fg. We can also say your Fn will always be larger than your Fay. But what if that applied force was upwards? Let's just do a what if quickly. Guys, change it over here quickly. So what if that Fay was up there? So yeah, just don't overthink it. Just use your F net is MA, which will be 0 in this case. And we can break it up, going up positive. So we then have Fn plus Fay plus a minus Fg, and that will be 0. So now you'll see that there's a slight difference. Now, which one will be larger in this case, the Fn or the Fg? So if you look at our equation, well, just logically, well, that shouldn't be there. Sorry about that. That's just looks like that. So that other vector wasn't supposed to be there. So which one's larger, the Fn or the Fg in this case? It will be the Fg, because those two together will have to equal that Fg. So logically, the Fg will always be larger. But you can just take a look at this equation also. Fg is the sum of these two. So therefore, Fg will always be bigger than the Fn in this specific case. If I just put random values in here, 2 plus 3 is 5, right? When will this value for Fn ever be greater than that Fg? It cannot be, right? So that's how you identify those. Okay, moving on. Well, what about this situation? Someone's pushing block B and it's moving the whole system to the left. What do we do with this? Well, let's draw the free body diagrams for A first. We don't overthink these. And maybe they'll ask you to calculate the acceleration of the blocks or how much force the one's applying to the other. But don't overthink it. Just draw the free body diagram and it should make a lot of sense. I'll do A with you and just plug B in by my... Oh, well, let's do B first, actually, because that's the... Okay, we assume friction exists. So this thing's being pushed to the left. That's an applied force. It's on a surface, so there's a, whoa, what was that? It has a normal, and it has a weight. And in this case, as opposed to the previous section, the Fg and the Fn will be exactly the same, of the same magnitude. And something else is happening to the right. That is your frictional force, but also there is another force at work here, because these two blocks are touching each other. The block A will provide some type of resistance to block B, which will be force A on B. It's going in the opposite. You're pushing this thing left. That block A is going to apply some type of force to the right. It's actually a Newton 3 thing, but it just will always happen. There we go. So that's the diagram for B, and let's look at A. So A has a force being applied to it to the left, and that is force B on A, not applied. The applied force is only in contact with that B block. Same as a Fn and Fg, and we're just going to assume friction exists everywhere. Right, so those are the two free body diagrams for these. It's kind of logical. So let's take a look at how these can be, if they ask you to work out the acceleration. Now if they want you to work out the, I just drew near the masses, just thumbsuck some masses for A and B. Mass for A is 1 and for B is 2 kilograms. Now they want us to work out the acceleration. Remember, we're dealing with Newton 2, so we don't overthink these things. So let's just look at the first one. F net is equal to ma. We know this is for A now, eh? And for B we'll do it just now. But let's look at A first. We're trying to work out acceleration. It's not accelerating upwards or downwards, so we're not going to look at these directly. We could have to, maybe have to look at those if they give us some frictional coefficient or something. But we are working in the x-plane, so we're only going to deal with those. Let's just take everything as right as positive. And as we said in the beginning of the video, we're going to break up this F net. So we have right as positive, so we have a positive friction plus a negative FB on A. Negative B on A, which is equal to MA, and for now we can substitute in from here. We have F, but let me just add something into this, so we're left with one unknown or two unknowns. Well, yeah, I think I'm not going to do that, but let's rather leave that. Just want to show you how to set these up. All right, so usually with these type of questions, you'll have two unknowns. You'll know your mass. You'll know the frictional force somehow. They might give you a kinetic friction coefficient of 0.2 or 0.8 or whatever. And then you can work out that Fk is equal to mu k n. You can actually just do this. But now your n will be equal to your Fg. So it can get a little bit, you can do it like a side calculation and just substitute it in. Or you can just use the formulas themselves. So this will actually be mu k mg if you're good at these type of things. So no m, we will not know acceleration, we will not know Fb on A, but we'll know g, m, and mu k, so we can find out that frictional force. Usually they can just give you the frictional force, or you'll actually have to work it out. Both are possible. But you can do that as a side calculation and just substitute it in for the frictional value. So we'll have two unknowns. So we'll have an F known, which we're looking over here. We have known F, we have known mass, and we don't know what the force B on A is, and we don't know what A is. So let's look at B. So we'll end up with some values there for frictional force, mass, but we'll have an unknown and an unknown over here. Looking at B, I'll just speed this one up. Right, so I have a negative applied force because it's going left, and we said right is positive, plus Fa on B plus friction is equal to Ma. Now, we won't know A, we will know M, we will be able to know friction, which and the applied force I will give to you, so you have then two unknowns there, and we will have to do a simultaneous equation. Now, I think I did say earlier, work out what A is. So what we have to do is, if they want the acceleration, then we will have to substitute this formula 1 into this formula 2, or vice versa. But we'll have to make that FB on A, or that FA on B. There will be this, that's actually the thing we should note. You actually have to identify this. They're in opposite directions, but the magnitude of them will be equal. So what we do then is, we can rewrite these formulas to put FA on B or B on A as a subject of one of them, and then substitute it into the other one. So let's look at equation number 1, and I'm just going to change the subject there. Right, there it is. I just took this and used algebra and put it in that format over there, so I had this by itself. So I can then substitute 1 into 2, and there's 2 over here, and I get then this. I'm going to write it down. Alright, so I just put those subscripts in there because I think that might confuse people. I think I might have overcomplicated this example, but this is how it works. Alright, so over here now you have your A's that will be identical. I probably should have done an example, but I don't want to redo the whole video. So yeah, let's go to the next one. I think it's that friction I added there might have been a problem. I should have maybe just done the actual example. I'll do this for the next one. But let's just see if we can. Yeah, I think I really overcomplicated this. But anyway, you'll know your frictions of the two objects. You'll know the applied force. You'll know the masses. So the only unknown here will be those accelerations, and you can work it out algebraically, and A will be equal to some value, and just indicate the direction after you work that out, right? Right, so what if you have a problem of an incline problem? So I'm just going to do a random case. Let's say this is 10 newtons. So we have a 10 kilogram block on a inclined surface. On an inclined surface, it's being pulled down with 10 newtons, and it's at an incline of 25 degrees. So how do we solve, and let's just say they want you to determine the acceleration of the system. So what do? Well, with these type of things, you want to draw a free body diagram, but I first like taking this diagram and just getting my things right. So I'll do a little, actually like more of a force diagram, but you have to then draw this perpendicular. This is the weight. So this is your weight. It's always downward, straight down. Doesn't matter what the surface is, but we're going to draw its components so that we actually need these so that we can solve the problem. Now this line over here will be your FG, and this is also FG, but which one's perpendicular to the surface? It will be this one over here, and the one that is, did I just say perpendicular or parallel? Okay, let me just read. Yeah, the one that's parallel to the surface will be this one. You see it's parallel. You guys remember parallel lines there? That's parallel to that surface, and this line is perpendicular to the surface. So that's your FG, perpendicular. And if that's 25, in this triangle, if 25 degrees, you can prove it if you want, but it will always be the case. So, oh, and by the way, you must be able to do these backwards. So if they give you a picture, oh sorry, that's actually if they give you a picture like this, you must be able to do this whole thing backwards. Okay. So there we have our triangle, and this is for our trigonometry to work out what our FG parallel is, because we need that to find out how this system accelerates. So they want to know what is the acceleration. And before we do that, like I always say, we have to draw a free body diagram. So we have an applied force of 10. Oh, I forgot to put the normal in. There's a normal as well, because it is on a surface. But remember, normal is always 90 degrees to a surface. We have some friction, because you're just assuming there's friction everywhere. And we have an applied force like this. So assume our friction is equal to 0, it's on ice, 1 Newton. Okay. It's going in the uphill direction. All right, so we have an applied force. For our free body diagram, we have some friction. And what else is happening in the x plane? We have an applied force, we have friction, and we have the FG parallel component. So we actually have to include that in our free body diagram, if I can draw it. All right. But what is happening in this is all in the parallel direction. We're going to call it the parallel direction. And in the perpendicular direction, we have the normal. And we have the FG perpendicular. Be those two, the FG perpendicular. So this is how you would draw it in a test or an exam. And you need this diagram to actually work everything out. So this object, I want us to determine the acceleration. This object is accelerating in which plane? Is it accelerating away from the surface? Is it going up and down? Is it levitating? No. It is accelerating in this parallel direction. So Newton to F net is equal to MA. And we have three vectors in the parallel plane. We have to choose a direction. Let's go uphill as positive. You can say negative, doesn't matter. But uphill is positive, so I have a positive friction plus a negative FA plus a negative FG parallel, and that will be equal to MA. We say the mass of this thing, yes. So let's just see what we can do here. Now the friction we said was 0.1, but and the applied force to be given is it's 10. Let's just maybe do this then. But we don't know what FG parallel is. We know the mass as well. We know what friction is. We know what the applied force is. So friction is 0.1. F applied is then 10 newtons. And FG parallel, we kind of have to use some trig over here by that triangle of that, basically that force diagram we drew over there, the pseudo force diagram. And we know the mass of the object, which was 10 kilograms. We want acceleration, so we can determine this with trig. So let's see. I'm just going to copy this diagram so we don't have to jump up and down. All right, there it is. So I'm going to erase all the parts we don't need, so we just can work with that triangle. There we go, erased. Now, what was that FG again? Well, it's 10 kilograms, and FG is equal to MA, or mg, sorry. And it says it's 10, and the gravitational acceleration is 9.8, so this will be a 98 Newton over there. Now we know this is 25 degrees, so looking at that angle, we want to find that opposite FG parallel for this specific equation. So is it going to be sine or cos? Remember, so sine is opposite over hypotenuse and cos is adjacent. So if we're going to go sine, we're going to go opposite over hypotenuse, which is what we want. If we go cos, we're going to get that over hypotenuse. We don't want FG parallel, so we can go sine in this case. If you somehow were crazy and you worked out the other one over here, and we're looking at that angle now, we can also say then, if we say sine of 75, we're going to work with the opposite side, which is not good, so we can actually go cos 75 is FG parallel over hypotenuse. Okay, but let's just go with that sine 25. So sine of 25 is equal to FG parallel over 98. So it's 98 sine of 25 is FG parallel. We can work this out and we get a value of 41.41658. Yeah, you can just put it in your memory or just don't round off midway through a thing. So we then take this up here and substitute it in. But let's just say you are really good at this and this is actually beneficial for your future, but this FG parallel, we can just directly from here figure it out. So you can actually say, just don't listen to this if you're not good at these things, or good at algebra, but I can just substitute that in as, even if we didn't work this out, it would be FG sine of theta, and FG is mg, and that will all be equal to that FG parallel. So you can actually bring this down and break it up into that piece there. Or not, just do side calculation and just sub that in. So we have F, which was 0, friction was 0.1, the applied force was it 10 newtons down, and our FG parallel was negative 41,41658 what, so equal to another 10 kilogram object and acceleration there. And we can solve for A. Just do your type in your calculator, remember A's and all this stuff divided by that. So yeah, I should actually maybe have done this a video already, made A the subject, but it doesn't matter. We can go this route and we get a value. Okay, so that's how you do those. Right, the last one I'm going to look at is pulleys. So pulleys, what's going on here? All right, pulleys. Now, when you think pulleys, think simultaneous equations, just like we thought with those blocks from earlier. Pulleys have to do with simultaneous equations because you got this tension here and this tension here, and you got acceleration and acceleration. So the tensions are equal and also the accelerations, and that will result basically 99% of the time or 90% of the time, unless they give you extra information, it will result in simultaneous equations. So just watch out for that. Now, let's look at this example here. Let's just say they want us to determine the acceleration. Again, they can also ask you to determine the tension. It's the exact same process. If they want the acceleration, then you must make T the subject of your substitutions. If they want the tension, then you make A the subject of your substitutions. So when you substitute A into the other A, because they'll be identical, and in the first case you substitute T into the other T of the other equation because they'll also be identical, because the tension rope's the same everywhere. Now, let's do this one. Let's just determine the acceleration there. First of all, free body diagrams of A and of B. I'll do this, just give them to you soon. Yeah, okay, let's do that quick. So for A, we have a friction left. It has a FG, it's on a surface, so it has a Fn, and it's being pulled to the right by tension, let's call it tension 1, and this is tension 2, and we have friction left. For B, it is in the air, so it has, or every object has a weight, anything with mass has weight. And does it have a normal? No, because it's not on a surface. But it has a tension pulling up, so it'll be T2. Okay. Now, we always have to draw free body diagrams, but with these type of questions, the very important part is what I'm about to do now. It's your positive and negative directions. You have to choose your direction like this. So this will be positive. So basically it is right is positive and down is positive. So just watch for that. Or you can say right is negative and down is negative. It has to be in this way. Right. So I know you want to say right is positive, up is positive, but don't worry about that. You have to do it in this manner. Otherwise, you can get your directions or can be buggered up. Okay, so let's take a look. For the first equation, for A, Newton 2 F net is equal to MA. And what forces are we looking at here? Here's our A. We are looking at the accelerating of A. Is accelerating up and down? looking over here, is it accelerating up and down? No, it's just going left, right. Its movement is in the x-plane or the horizontal plane. So we're just going to look at those in the x-plane, which will be those two. So it breaks up. We said right is positive, so we have T1 plus a negative f is equal to ma, or we're just going to say T1 minus f is ma. And our values are, we don't know what t is, we know what f is, we're going to say 0,1. I just thumb suck these values. I hope it doesn't mess up our directions, because it can. And the mass of the object is 1, a, it's just a, so it's T1. So a is equal to T1 minus 0,1. That's acceleration. And for b, we said then, is up positive or down positive? We said down is positive. It has to be like that. Again, F net is ma. And F net will break up into down being positive. We have Fg is a positive, and plus a negative T2 equal to ma. Let's just make this nice and tidy. Oh, Fg, I can break that up as well. Fg is equal to mg. You can do a separate calculation. I think most people will prefer that in grade 11. But Fg isn't, Fg is equal to mg. Cool, eh? So you're going to say whatever Fg is, replace it with what it's equal to. Can do that. It's not a difficult one there. So the previous ones were quite involved. All right, and so let's put in some values. So the m for b was a 2 kgs, right? And it's 9,8 is your g value, your gravitational acceleration. And the m is 2, and the acceleration we don't know. Let me solve this quick, or simplify. Well, there we go. But we have to determine a. We want a. We're not going to do a simultaneous equation here using a. Because if you do that, we're going to end up with a value of tension, which you can then substitute back in, but you're making more work for yourself. And then it's not a big issue, but like time is of the essence in an exam. So they want us to determine a, so we're going to substitute t. We're going to make t equal to each other. So let me just rearrange one of these equations, so we can do that. Okay, so I did it over here. I just rearranged, and that will be then equation 1, and this will say, we'll say is equation 2. And we just make a note here, T1 is equal to T2. Therefore, we're going to substitute in. So we're going to put 1 into 2. 1 into 2. So we have, writing the second equation, we have 19, 19,6 minus T2, but we're going to put T1, substitute equation 1 into equation 2, because these two tensions are identical in magnitude. So we substitute it in. We leave that negative outside. We don't mess with that. We're just going to deal with that T2, and we're going to substitute in the brackets. So T1, which is equal to T2, will be equal to that value, a plus 0,1. And that will be equal to 2a. So you see, I took this equation. So over here, I rewrote it, but I substituted that T2 with whatever that T1 was, which is that. And I left that negative on the outside. Alright, so let's simplify. 2a, 19,6, watch out your negative on the outside there. So you have negative a, negative 0,1. And I'll just solve this quick. Right, yeah, I solved it. And we have a value of 6,5, and I wrote here 6,5 meters per second. No. Meters per second squared. Watch out for that. So that will be my acceleration, and it will be, if you go up here to the diagram, it will be in this general direction. So every second that elapsed, that thing will move 6.5 meters per second faster. That's quite quick, so quite an acceleration there. Okay, so that's how you work these out. Right, that will be the end of this video. I hope it helps. Hope it helps you understand. Let me know if you have any further queries. I can do another video on that. Wait, one thing I want to mention is that you mustn't mess with, in all these equations, Newton 2, F net is equal to ma. This is actually important. do not mess with this A sign. This will be like an absolute value. M mass will always be positive, and your acceleration will just, when using this equation initially, will always be a positive value. Your directions are indicated by your net force on the left here. All right, here we go.